Hey everybody, how are we doing today? Hopefully y'all are doing well. So today we will be actually finishing our notes on bonding. Okay, now for this, please make sure you've got your periodic table and everything else that you will need for the lesson. But otherwise, we're going to go ahead and get started. Now, today's focus of the lesson is on polarity. So what is polarity? Well, polarity is basically us looking at a molecule and deciding, or a bond, and deciding what's going on with that in terms of positive and negative charge. Now, ultimately, a lot of times students are asking, well, why is that really important? Okay, it's going to tell us if something, for instance, like water, will dissolve certain substances. If you take salt, table salt, NaCl, and you put it into water, does it dissolve? Yes, it does. Whereas if you take something like wax and you put it into the water, does it dissolve? No, it doesn't. Well, why does it not? Again, that has to do with polarity. When we talk about polarity, it is like dissolves like. So if something is a polar molecule, it will dissolve another polar molecule. If it's a nonpolar molecule, it will dissolve a nonpolar substance, okay? And so a lot of times I'll say, okay, well, if I take something like gasoline or acetone and I put like a styrofoam block into that, it will actually dissolve. Whereas if I take that same styrofoam and I drop it into water, it will not. Same thing can be said about table salt. If I take table salt and I drop it into water, it will dissolve. Whereas if I drop it into something like acetone, it will not. Why? Because there are differences in polarity. One is polar, one is nonpolar. So for polarity, the very first thing that we need to know how to do is determine the polarity of a bond, specifically in a compound, right? And so what we're doing is we're going to actually be looking at their differences in electronegativity. Now, for that does mean you need to be able to think about your electronegativity. And if you're not given this table right here, what you need to do is recognize what your general trend is. So if I take my periodic table, remember my general trend is that if I'm starting at fluorine, as I move down away from fluorine, it's going to decrease by 1. And as I move across the periodic table, it's going to decrease by 0.5. So if I were to ask you, what is the polarity of something like nitrogen? Remember, we start at 4 for fluorine, and we're going to go over 1, 2, right? So we go over from fluorine over to oxygen, and then we go over to nitrogen. So we're moving across 2 times, which means our electronegativity is going to decrease by about 1, right? So 0.5 for each time you move left. And so if it decreases by about 1, then nitrogen's electronegativity is about 3. Well, if you look at your table of electronegativities, you see that that is also the case. Now, again, that general trend is not perfect. We do know that sometimes it does not work that way. But the general trend is sometimes all you have. And so that's what we're going to use if you're not given this table. Okay? Now, for this, we do need to determine what the electronegativities of substances are, and we're going to compare their differences. If their difference is between 0 and 0.39, so right here, then we would classify that bond as a nonpolar covalent bond. If the bond is between 0 or 0.4 and 1.69, we would call that polar covalent. And last, if it's between 1.70 and, well, on, then we would classify that as ionic. Now, if you notice, sometimes when we looked at something and we had a metal and a nonmetal, we said that it was not actually ionic. You saw that on one of your notes for this unit with that beryllium chloride. Why was that? Well, their differences in electronegativity was not high enough. And so because of that, we classified it as a covalent bond, right? And so that's looking at these differences in electronegativity and determining what kind of bond has formed. So what do I ultimately need to do with this? Well, remember that when we talk about like an ionic versus a covalent bond, we say that ionic transfer electrons. Well, looking at your differences in electronegativities, you can kind of see why, right? There's such a big difference in their electronegativities that you start to see those electrons pulled much further across, much further away from one substance towards another substance. Versus the polar covalent, you're going to see them pulled a lot less far, a lot smaller distance, because there's a smaller difference in electronegativity. So that's ultimately what we're talking about when we're talking about those bond polarity. Is the bond polar or is it non-polar? So let's actually move on down. If we talk about hydrogen and fluorine, fluorine has an electronegativity of 4. Hydrogen has an electronegativity of 2. What that tells me is that those electrons are going to be pulled much closer to fluorine over the hydrogen. Why? Because fluorine has such a high electronegativity that those electrons get pulled towards it. Okay? And so when it happens, when we do that, so we have our hydrogen and our fluorine, so the electrons are going to move towards fluorine, right? Well, what that does is that makes this fluorine slightly negative, and that makes this hydrogen slightly positive, because we've got that movement of electrons moving from one side of the compound to the other side of the compound. Now, again, essentially what we're looking at is the greater their difference in electronegativity, the more polar the bond actually is. Okay? So, just because we have polar bonds doesn't necessarily mean that a molecule is polar. Now, this is where those Vesper shapes are very, very important. You've got to know what the shape is, because the shape could also determine the molecular polarity as well. And so that's something that we're going to need to look at. That's something that we're going to do in our lesson today. So first off, we need to determine the polarity of the bonds. So my first question here is, what type of bond is found in bromine? Now remember, bromine is a diatomic element, so Br2, and we've got a bromine, and it's attached to another bromine. Now, I'm not going to draw anything more because this is going to be linear, right? Why? Because there's only 2 elements there. And so looking at this, I need to figure out what is the polarity of this. To do that, I need to know their electronegativities. So I look at my periodic table. I see that bromine is 2 down below fluorine. So bromine 1 has an electronegativity of about 2, and bromine 2 has an electronegativity of, again, the same, 2. So their difference in electronegativity is 0. Well, if it's 0, then that would tell me that the bond polarity is nonpolar covalent, right? So we would have one nonpolar covalent bond. Okay, so again, what we do is we compare their differences in electronegativity, and then from that, we're going to determine what the polarity of the bond actually is. Okay, so next we've got methane. So methane is CH4. And for our Vesper shape, we've got a carbon with a hydrogen, a hydrogen, a hydrogen, and another hydrogen. So you're like, okay, well, if I've got to determine what the polarity of the bond or bonds are, which bond am I talking about? Well, I'm talking about all the bonds. So I need to determine the polarity of the bond between that carbon and hydrogen, that carbon and hydrogen, that carbon and hydrogen, and that carbon and hydrogen. So I need to look at all the bonds and determine the polarity of every single bond. So let's do that. So carbon has an electronegativity of about 2.5. Hydrogen has an electronegativity of about 2. Technically it's 2.1, but we're going to go with 2 because we're going to use that general trend. We find the difference. We have a difference of 0.5. So let's come back up here to this chart, and we see that if it's between 0.4 and 1.69, that bond is a polar covalent bond. So it's a polar covalent bond. Okay, so I know that the carbon to hydrogen bond is polar covalent. And how many of those do I have? Well, I have 1, 2, 3, and 4. So I have a total of 4 polar covalent bonds there. And then that would be my answer there. So what type of bond? There would be 4 polar covalent bond. And then last I have my pH3 here. My Vesper shape for that is going to end up being like this, which based off of your Vesper notes, you should recognize that as trigonal pyramidal. Because we have that lone pair, and remember, lone pairs are very repulsive, and so they're going to push everything else away. Okay, and this would be that shape that you have. Okay. All right, so now I need to compare, and we need to find how many of each type of bond I have. So I've got 1 bond here, 1 bond there, and 1 bond there. So I've got a total of 3 bonds that I'm working with. They're all the same type of bond. So I have phosphorus. Phosphorus has an electronegativity of about, let's see, we start at fluorine, which is 4, down to chlorine, which is 3, and then we go over 2, which means we would go over by 0.5 for each one. So 3 down to 2. So phosphorus is about a 2.0. Hydrogen is also about a 2.0. So my difference is 0. And so what that tells me is that I have 3 nonpolar covalent bonds. And that would be my answer there. All right. So again, when we talk about polarity, remember it's just meaning that electrons are going to move closer to one side over the other. And so because they're moving closer to one side, you're going to end up with a side that is a little bit positive or kind of positive or slightly positive. And then we would also end up with a side with it that is a little bit negative, slightly kind of right. Okay, and so we're looking at those and we're just seeing which direction those electrons are going to be moving. And we do signify that slightly or partially with this lowercase delta, which I kind of look at it as you've got an S and you just kind of loop it off on the end. So S for slightly, and that's how I've always remembered it. So slightly positive or negative. So slightly positive versus slightly negative. All right, now, the presence of a polar bond may or may not determine if the molecule is polar or nonpolar. Now, here's the thing, y'all. If all the bonds are nonpolar, then yes, the molecule itself will also be nonpolar. But just because the bonds are polar does not mean that the molecule has to be polar as well. What does it mean to be polar? Well, remember that polar means you've got one side positive and one side negative. So you have to have a side that is positive and a side that is negative. So let's first off, before we actually dive into that a little bit more, let's do one more quick practice on water. So what type of bond is found in water? Now remember, the shape of water is hydrogen bonded to an oxygen bonded to a hydrogen. There are 2 lone pairs there. Looks like my computer messed up on me a little bit. So 2 lone pairs there. And so we would get this bent shape right here. Now, what type of bonds are found there? Well, I'm comparing oxygen to hydrogen, and there are 2 of those bonds. So oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of about 2.0. We find their difference, and we find that is 1.5. So our difference in electronegativity is 1.5, which tells me that that bond is a polar covalent bond. So I have 2 polar covalent bonds. Now, how many nonpolar bonds are there? Well, there's only 2 bonds that are present, and since both of those are polar, then you would have 0 nonpolar bonds. So 0 nonpolar covalent bonds. Okay, and so that's what my question was asking there. So now let's actually look at a molecule, okay? And we're going to start with a little bit more complicated one because it's got a little bit more complicated Vesper shape. So it says how many bonds, polar bonds and nonpolar bonds, are there in C2CL6? Now with this one, it's a little bit more complicated because you're going to actually have two central atoms because you've got that carbon. I'm going to be honest, your carbons are going to be the ones that you form that what we call a carbon chain, where those carbons are all going to be lined up connected to one another. Now, they also want to know, is the molecule itself polar? So let's first off draw our shape. So I have carbon bonded to another carbon, and then we've spread out our chlorines. Just like that. And then you would need to go in and fill your outer octets. So 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And we do that for all of these. All right. Now, remember that you would needed to have counted up your valence electrons for each thing, added it together, and then your total number should equal this. Now, I have already done that for y'all, so you don't need to worry about that in this case. But when you're doing your tests and stuff, you will need to make sure that you are doing this as well. Okay? All right, so now what I need to do is, first off, look and see what bonds I have that have formed. So I've got a bond between carbon and chlorine, one there, one there, one there, one there, and one there. But then I also have a bond between my carbon and carbon. So there's two different types of bonds here, and we do need to make sure we keep note of that. So for my carbon to chlorine bond, carbon has an electronegativity of about 2.5. Chlorine's electronegativity is about 3. So their difference in electronegativity is 0.5, which does tell me that that is a polar covalent bond. All right, so I have, looking back at my pink highlighting here, I have 1, 2, 3, 4, 5, 6. So I have 6 polar covalent bonds. How many nonpolar? Well, now I'm comparing my carbon to carbon bond. So carbon to carbon. Carbon has an electronegativity of 2.5. The other carbon has an electronegativity of 2.5. So my difference is 0. So that means I have one nonpolar covalent bond. All right, now I need to figure out if the molecule itself is polar. So how do I do that? Well, essentially what we're going to do is we're going to go back and we're going to label all of our polar bonds. So we know that the carbon to chlorine bond is a polar bond. So what that tells me is that electrons are going to move. They're going to move towards the thing with the highest electronegativity. So here, my electrons are going to move towards chlorine, right? Because chlorine has an electronegativity of 3 versus carbon's electronegativity of 2.5. So what that does is that makes this chlorine side slightly negative. And that makes my carbon side slightly positive. And we do that for all of these. Slightly negative, and it's going to move out, slightly negative. And last, we're going to move up here, slightly negative, with that carbon being slightly positive. Okay? And nonpolar, we don't need to recognize that in terms of polarity because it's nonpolar, right? Now, I need to decide if this molecule is polar or nonpolar. So in terms of looking at this, I see on the outside, everything is negative, right? Remember that to be polar, you need one side positive and one side negative. In this case, all sides are negative. And so since all the sides are negative, our molecule, so the molecule is nonpolar. Okay, so then this, all of this would be what the question was ultimately asking for. Okay, so now we've got, so we know that that one was nonpolar, so let's take another look at another substance. So again, what we need to do, we need to start with all of these, is to draw their Lewis structure. So how many polar bonds and how many nonpolar bonds are there in C2F4? Is the molecule itself polar? Okay, again, start with my Lewis structure. So I have a carbon bonded to a carbon, and then you've got your fluorines that are spread out around those. Okay, now here's the thing. We actually need another bond there in between those carbons, and that's how we are going to get that extra 8 electrons on each of those central atoms. So then we would go in and fill our outer octet. And up here. Okay, so now let's take a look at the bonds. Let's see what is polar, what is nonpolar, if any, right? So I have, first off, carbon to fluorine bonds here. So that's right here, right here, right here, and right here. So there are 4 carbon to fluorine bonds. And then there is also a carbon to carbon bond right there. Okay, so we do have 5 different bonds that we're looking at. So for the carbon to fluorine bond, carbon has an electronegativity of 2.5. Fluorine is 4. So their difference is 1.5. Again, that tells me that that is a polar covalent bond. Then we have the carbon to carbon bond. Carbon has an electronegativity of 2.5. The other carbon is 2.5. So their difference is 0. So it's nonpolar. So I have 4 polar covalent. And that's for each of those carbon to fluorine bonds. I have 1 nonpolar covalent. And then let's take a look at our molecule itself. So we know that the carbon to fluorine bonds are polar. So those electrons are going to move towards fluorine because fluorine has a higher electronegativity. And so that would make the fluorine slightly negative, slightly negative, slightly negative, and slightly negative, because all of those, we're going to have those electrons moving towards the fluorines, which would make our carbons slightly positive. Okay, so on the outside here, what do we notice? Well, what we should notice is that everything is negative. So again, what that tells me is that my molecule is nonpolar. Okay, so we're going to go ahead and move on to the next page. And I'm going to do this ammonia down here at the bottom. I'm going to leave those other 2 for you to do as practice. So I have ammonia. Ammonia is NH3. So ammonia, normally when we would draw its Lewis structure, would look like this. But remember, we've got a lone pair there. So when you have that lone pair, what do we know? Lone pairs are very repulsive, so they push everything else away, right? And so this turns into this. Okay, so we know that we've got this trigonal pyramidal shape, okay, because you got your lone pair here, and then you've got your 3 different hydrogens coming off the bottom. So now I need to decide whether or not this molecule is polar or nonpolar, and they also ask me how many polar bonds. So they don't even say how many nonpolar bonds, so we don't need to worry about that. So how many polar bonds are there? So I have nitrogen to hydrogen, and there are 1, 2, 3 of those. So I have 3 nitrogen to hydrogen bonds. So nitrogen has an electronegativity of about 3. Hydrogen is again about 2. So their difference is 1. Now that means that this is a polar bond. So we have 3 polar bonds. Okay. And they are specifically polar covalent bonds. Should have added that. Polar covalent bonds. Now, what I need to do is I need to see, is the molecule itself polar? So for that, I need to keep in mind what direction those electrons are moving. So in this case, nitrogen has a higher electronegativity, so those electrons are going to move towards nitrogen, which would make it slightly negative and the hydrogen slightly positive. Again, moving towards my nitrogen, making it slightly positive. And then this last hydrogen moving up towards that nitrogen, making it slightly positive. Now, looking at this molecule, we have one side negative, so the top is negative and the bottom is positive. So what does that tell us about our molecule? One side positive, one side negative. So the molecule is polar. Okay, so the molecule is polar here. Now, here's what I want to point out. If you had forgotten to adjust your shape based off of those lone pairs, if you had forgotten to do your Vesper shape, your molecule would have been nonpolar. Why? Because you would have had a slightly positive, slightly positive, slightly positive, and you would look at this and you'd be like, okay, well, everything on the outside is positive, right? And so because of that, you would say, okay, well, this must be nonpolar then. Well, but remember, when we change that shape because of those lone pairs, it actually reveals that central atom. It reveals that nitrogen. And so it makes that negative side be exposed. And so we have a negative side and a positive side on our molecule, which makes the molecule polar. Okay? So just keep that in mind. It's important that you adjust the shape just to help reflect that change in polarity. Okay? All right, y'all, that is it for our notes on polarity. As always, let us know if you have any questions. Don't hesitate to reach out. But otherwise, y'all have a great rest of the day. Bye, y'all.